minutes. There were two problems that I posted on my blog, which were related to the multiplication principle. And the first one involved an imaginary scenario in which a teacher had 26 students, and all of their initials came from the set A, B, C, D, E. So some students could have BB, CA, AC, etc. And the question is it possible for all students, all 26 students, to have different initials? Okay, that's the question. Now, there's a logically equivalent way to express that question. Another way to say that, and this is a little more sophisticated, is if the answer is no, that means it is not possible, then that would be equivalent to saying that at least 2 of the 26 students must have the same initials. Now you have to think about that. That is something we can discuss more, and it's related to the pigeonhole principle. But for now, we're going to get right into demonstrating that it is not possible because there are only 25 different sets of initials. Here's how we can do this. As I recommended the other day, listing is still the most powerful method. Making an organized list, even if there were thousands of possibilities, starting out the list and recognizing a pattern would enable you to solve the problem without sophisticated mathematics. And I think a lot of students would write AA, AB, AC, AD, AE. The younger students tend to be more scattered. We hope as they move up, they will become more organized, and they need models like this to follow. So the first initial could be A, and then there are 5 possibilities. The first initial could be, excuse me, B, and then there are 5 possibilities, 5 different initials. And notice it's very important to see that these are different, A, B, and BA. Similarly for C, D, and E. So you have 5 groups of 5. And this is how I developed or recommended you develop motivating multiplication. 5 groups of 5 each. So we have 25. And this could very easily be demonstrated with the slot method, but let me just review the conclusion. If there are 25 different sets of initials possible, and there are 26 students, then it is not possible for all 26 students to have different initials. So we're going to move on, and instead of the listing method, we're going to do the equivalent. First initial, last initial, write down the possibilities for each initial, A, B, C, D, E. Put the number of possibilities, that's what this is, the number of choices. And then do the same for the second initial, last initial, A, B, C, D, E. We multiply, and again we get 25. So this is the shortcut. Now I want to review the multiplication principle a little bit. Complicated problems in mathematics, far more complicated than this, would often involve many steps. And what we try to do is break down these compound events, meaning choose an initial, then do something else, choose a second initial, or then do something else, and then do something else, anytime you have problems like that, we like to use the multiplication principle because it allows you to determine the number of outcomes one event at a time. So the first event is select the first initial. After that has been done, then we select the second initial, and again, there are 5 ways. And what's important there's a mnemonic to help you memorize. I use this for students frequently, and some remember it, and some don't even take notes unless I'm standing over them. At least this was true in the past. Anyway, whenever they see the phrase followed by in a counting problem, it'll remind them to multiply, followed by multiply. If the phrase followed by is not in the problem, they should try to rephrase the question, see if it's possible. But usually something like this is in the problem. First do this, then do this. After you've done that, then do something else, and that's easily rewritten as followed by or rephrased. So remember this, followed by multiply. Okay, so now we're going to move on to the second question, and I have less than 3 minutes to complete this, so I'm going to go faster. Again, a teacher is involved, and this time the teacher has 5 classes, a total of 129 students. This was on my blog post from the other day. It was the second problem. And he wants to assign a unique color code to each student consisting of 3 colors. Repetitions are possible. So, and he's choosing from red, I forget the colors actually. I think it was red, blue, green, yellow, purple. That's it. And he's going to choose a color code in sequence like this. Blue, blue, red. Or blue, red, blue. Or green, yellow, purple, and so on. I always recommend to students, and I think it's a very strong heuristic for teachers to use in the classroom, have them list a few possibilities, because if they have trouble understanding what the question is talking about, and the problem doesn't give examples, which happens, then they have to make up their own examples, and then they could reverse the order and see if order counts. We'll come back to this. It's very important to do that. We can make an organized list. We could start with red and list all the code combinations with red, 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 blue, red, red, green, etc. But this is a problem that's begging us to use the multiplication principle. Although this will work, it's cumbersome and it is time consuming. So we will use a multiplication or slot method. Red, blue, green, yellow, purple. So there are 5 choices for event number 1. Choose first color. Followed by, there are 5 choices for event 2 because we can use the same letter. And 5 choices for event 3, followed by multiply. So there are 125 unique codes. Once again, the number of students is greater than the number of different, not initials this time, but codes. So it is not possible for him to do this with those 5 colors. He'd either need more colors or ask a few students to leave. Anyway, oh, I dropped my marker here. I'm over 10 minutes, so I have to stop right here. Thank you.